In this video, I'll talk about catalysts. There are two very important facts about catalysts. First, a catalyst speeds up both the forward and reverse reactions to the same extent. So if a catalyst doubles the forward reaction rate, simultaneously, it doubles the reverse reaction rate. A catalyst never increases the yield of the production. It just makes the production faster. Second, a catalyst is neither consumed nor produced in the reaction. Let's watch this video.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 44. It's on catalysts. Catalysts can speed up a reaction, but they're not consumed in the reaction. One of the greatest chemistry demonstrations is elephant toothpaste. And I'm going to put a link right here to a video. This is from Brian Swarthout, a friend of mine, and his son Sam is doing the elephant toothpaste demonstration. Essentially, you add a catalyst to it, and then you have this reaction go really, really quickly. And so please give that a watch. Brian makes some wonderful videos in chemistry and physics. I'll put a link to some of his stuff down below. But how do catalysts work? Well, essentially they speed up a reaction. Some catalysts actually slow down reactions, but in general they're going to speed it up by lowering the activation energy, the amount of energy we have to put in a system before we can stress those bonds, break them, and form new bonds. And so it has to go through this transition state, but a catalyst can stabilize that transition state, and therefore it can lower the activation energy and it can speed that reaction up. Now, some catalysts will actually add new intermediates. In other words, they're going to add new steps in this overall reaction mechanism. And so if we look at the energy profile of a reaction, remember we've got reactants on one side and products on the other. This would be an exothermic or an exergonic reaction. And so essentially we've got reactants, we've got products, but if we want to move between the two, we have to add a little bit of stress to those bonds. In other words, we have to achieve this transitional state. Eventually we can break those bonds and we can form new bonds. And so let me show you a catalyst at work. This is catalase, which is an enzyme found in almost all living cells. So what I'm doing is adding a little bit of hydrogen peroxide to a bag that's got yeast in it, and you could try this at home. Shake it up a little bit and you can see I'm producing a huge amount of oxygen gas right there. And so hydrogen peroxide would do this on its own, but if we add an enzyme to it, we can speed that whole process along. So how does it do that? If we look at the reactants on the left, that's going to be hydrogen peroxide, and the water and oxygen on the right, we see that we have to get through a large activation energy. And so what does catalase do? Well, scientists think there's a heme group in the middle of it, and that means just it's a number of atoms, but it's got iron right in the middle. And what that iron's acting to do is to pull one of those oxygens away. So it's stressing that bond on the hydrogen peroxide, and it's stabilizing this transition state, so it's more likely to fall into that just water and oxygen. Again, it's going to release energy, but if we look at the energy here, and if we look at the energy here, the net amount of energy that we're getting out is going to be the same. That catalyst is just acting to lower the activation energy. Now, sometimes it works by creating new intermediates and new steps in the reaction. And so in this elephant toothpaste experiment, you're taking concentrated hydrogen peroxide and soap, and then we're adding potassium iodide to that, and that's simply going to act as the catalyst. Now, what's it doing? That iodine is going to grab one of the oxygens, so it's going to make this intermediate, which will then bond with the other hydrogen peroxide, and that's going to create water and oxygen. And so we're really breaking a one-step reaction into two steps, and then we've got a new intermediate here. Well, what does that look like on an energy profile? This would be our original energy profile. We got reactants on one side, products on the other. But if we look at this two-step process, what we're doing is we're actually lowering the overall activation energy by doing two steps. In the first step, we're freeing up that oxygen, then we're bonding it to the other hydrogen peroxide to make water. And so we've lowered the overall activation energy of that reaction. And so did you learn to translate energy profiles? That's what this is right here. Particulate representations, and then even symbolic representations for chemical reactions with and without a catalyst. I hope you did, and I hope that was helpful.
All right, let's get back to the document. I have a simplified energy profile here. And over here, I'm going to emphasize a few things. So first, let's look at the reaction between A and B. It's a reversible reaction. So you can go from A to B, and you can go from B back to A. But either way, you need to overcome A energy barrier. So from A to B, the energy barrier is this much. So that's the energy difference between A and this transition state. And from B back to A, you need to overcome even larger energy barrier, all the way from B all the way up to here. So that's a very large energy barrier. By adding a catalyst, you are changing the reaction profile or energy profile to this. Okay, this is without a catalyst, a huge bump. With a catalyst, you form a intermediate here and then go from intermediate to the product. You are getting two bumps. Both are much smaller than the initial energy barrier. So it's a so-called sequential reaction mechanism. You have the first step here, the second step here. The second step has slightly larger energy barrier. So I'm going to call this the rate limiting step of this catalyzed reaction mechanism. But still, if you compare this to energy barriers with this one, overall, you drop the energy barrier from here all the way to here. And it's not just the forward reaction barrier. Again, if you look at the forward reaction barrier, you go from here to here. So the decrease is this much. This is a huge decrease of the reaction barrier in the forward direction. Now let's look at the backward direction. We go from B to A. Without a catalyst, you need to overcome this barrier. With the catalyst, you need to overcome, okay, from here to here, this much. What's the difference? The difference is also this much. Again, adding a catalyst decreases the forward energy barrier by this much, and also it decreases the reverse reaction energy barrier by the same amount. Therefore, adding a catalyst increases the forward reaction rate and reverse reaction rate to the same extent. In the middle, we have this intermediate here. This is the summary. The typical catalysis mechanism is this. The catalyst reacts with the reactant to form intermediate, and the intermediate becomes the product plus the catalyst. Therefore, catalyst is not really consumed in the reaction. And don't forget, it can also go backward. The catalyst can react with this B to form intermediate, the same intermediate. And this same intermediate may decompose back into A plus C. Again, C is neither consumed nor produced in this reaction mechanism. And don't forget about the backward direction. Two more concepts: homogeneous catalysis versus heterogeneous catalysis. Homogeneous means only one phase, so the entire reaction, the reactant, the product, and the catalyst exist in the same phase, for example, in the liquid phase. Alright, so everything is a liquid. And also we have heterogeneous catalysis. That means we have two or more phases being involved. For example, if we use iron to catalyze this reaction between nitrogen and hydrogen to produce ammonia, this is a heterogeneous catalysis because iron is in the solid state. Nitrogen, hydrogen, and ammonia are in the gas states. So there are two different phases. There's a solid phase, there is a gas phase. Therefore, we call this catalysis heterogeneous catalysis. All right? Now let's look at one practice problem. So let's say we have a reversible reaction mechanism. So we can go from A to B and B back to A. Okay? There are two elementary reactions here. Again, the forward A to B and the reverse B to A. So now we add a catalyst into this reaction system. Let's say the catalyst increases the forward reaction rate tenfold. Now my question is this: how does the reverse reaction rate change? And how will this catalyst affect the equilibrium concentrations of A and B? The first question is easy because, again, you just need to remember the catalyst increases the forward and reverse reaction rates to the same extent. So you just need to say, well, the reverse reaction rate also increases tenfold, exactly the same as the forward reaction rate. All right? Both increase tenfold. And 2, adding the catalyst has no effect on the equilibrium concentrations of A and B. Absolutely no effect. Let me explain. Without the catalyst at the equilibrium, we have Kf times the concentration of A equals Kr times the concentration of B. So this Kf times A is the forward rate. Kr times B is the reverse rate. Now, I'm going to increase both the forward and reverse reaction rates tenfold. So you have this 10 times Kf. This is a new reaction rate constant for the forward reaction. At the same time, the reverse reaction rate constant is 10 times Kr. So at the equilibrium, you have simply 10 times Kf times A equals 10 times Kr times B. You see this equation and this equation give you the relationship between the concentration of A and the concentration of B. But by looking at these two equations carefully, is there any difference? There's no difference. A over B at equilibrium is simply Kr over Kf. B over A at equilibrium is simply Kf over Kr. Okay, it's called cross multiplication, I believe. But anyway, in the end, if you use this equation with catalyst, B over A is, again, Kf over Kr at the equilibrium. This 10 and this 10 cancel. So, in the end, the catalyst does help the reaction reach equilibrium faster. And in this numerical example, 10 times faster. However, the catalyst never changes the equilibrium concentrations of the reactants or the products.